Hello, good evening, everyone. I hope you have enjoyed the last class on earthquake. So now we will discuss some more parameters regarding earthquake. In the last class, we have seen equivalent lateral load method, or what you can say equivalent static force method. So it was in, I guess, in the module 2 it was there. I am just opening it. Wait. So these we have seen, that is how the derivation part is being done, that we have seen. So now we will solve a problem on this using the available data. We will solve a problem on it. I am sharing the screen. I hope it is visible to you. If not, you tell me. You just place your queries in the comment box if you are unable to see it. So in the last class, we have seen equivalent static method, or equivalent, what you can say. This we have seen. It is response spectrum method, detailed procedure, dynamic analysis, and also equivalent static force analysis we have done. So now what we will do is we will solve a problem. So the plan and elevation of a four-story reinforced concrete building is as shown in the figure. The building details are as follows. The number of story is 4, zone is 3, live load is 3 kilonewton per meter square, column size is 450 into 450 mm, beam size is 250 into 400 mm, thickness of slab is 150 mm, thickness of wall is 120 mm, importance factor is 1.0, structural type OMRF building, determine design seismic lateral load and storage shear force distribution. This you have to determine. One app is trying to just open. I will just close it. Okay. Hmm. So what you need to determine? You determine design seismic lateral load and storage shear force distribution. So this is the figure, this is the plan, and this is the elevation. So we'll start the analysis part. So the solution contains analysis considering stiffness of infill masonry. So how we are calculating computation of seismic weights. Assuming unit weight of concrete as 25 kilonewton per meter cube and 22.5 kilonewton for masonry. So what we are assuming? We are assuming the unit weight of concrete as 25 kilonewton per meter cube and 22.5 kilonewton per meter for masonry. For slab, so how to calculate the dead load? Dead load due to self weight of slab. It is nothing but 22.5 into 22.5 into 0.15 into 25. So it comes out to be 1898.40. So this figure also will be helpful for solving the problem. Now beams. So in case of beams, how you are calculating? Self weight of beam per unit length is equal to 0.25 into zero point 0.4 into 25. So this comes out to be 2.5 kilonewton per meter. We are multiplying with the density of concrete also. So the total length comes out to be 4 into 22 into 5 into 2. So it comes out to be 180 meter. Now the dead load due to self weight of the beam. Dead load due to self weight of the beam is how much? 2.5 into 22.5 into 4 into 2. So it comes out to be 450 Newton. Now columns. Self weight of column per unit length. So how much is the self weight of column per unit length? So it comes out to be 0.45 into 0.45 into 25. So it comes out to be 5.0625 kilonewton per meter. And dead load due to self weight of columns, it is how much? 16 numbers. So 16 into 5.0625 into 3. So it comes out to be 243. Then walls. self weight of wall per unit length 0.12 into 3 into 20. So it comes out to be 7.2 kilonewton per meter. Now the total length will be equal to 4 into 22.5 into 2. So it comes out to be 180 meter. Now the dead load due to self weight of the walls is how much? 7.2. This is what we have calculated, self weight into 22.5 into 4. So it comes out to be 648 kilonewton. Now the live load or imposed load, it is 25% of the that load. So how much it will be? 0.25 into 3 into 22.5 to 22.5. It comes out to be 380 kilonewton. Now load on all floors. W1 is equal to W2 is equal to W3. How much it is? 1898 plus 380 plus 450 plus 243 plus 648. So it comes out to be 3619 kilonewton. Now the load on the roof slab, that is live load on the slab, is 0. So how much will be W4 equal to 1898 plus 0 plus 440 plus 243 by 2 plus 648 by 2. So it comes out to be 2793.5 kilonewton. Total seismic weight W is equal to 3619 into 3 plus 2793.5. So it comes out to be 13650.5 kilonewton. Now the fundamental period, natural period T is equal to 0.09 into h by d, h by under root d equal to 0.09 equal into 12 divided by root of 22.5. So it comes out to be 0.227. So moment resisting with frame with infill walls. Now the spectral acceleration type of soil is, we are assuming the soil to be medium soil. For TA equal to 0.2277, SA by G is equal to 2.5. Now zone factor for zone 3, Z is equal to 0.16 and importance factor I is equal to 1.0 and response reduction factor is equal to R equal to 3.0 for OMRF building. Now the horizontal acceleration coefficient AH is equal to Z into SA into I divided by 2GR. So it comes out to be Z moment 0.16, SA is 2.5 into and 2 into R is 1 by 3. So AI comes, H comes out to be 0.0667. Now the base here VH is equal to AH into W. AH is 0.0667 into W is 13650.50. So it comes out to be 910. Slowly lateral forces and shear forces are calculated and tabulated in the following table. So 1, 2, 3, 4 is the floor level, and these are the loads in kilonewton, and these are the values of HI. So WI HI is equal to this much. So the story forces QI is equal to VB into WI into HI square summation of WI square. So story shear force cumulative sum, it comes out to be this much. Storage shear forces are calculated as follows. Last column of the table, that is V is equal to Q4 is equal to 426.53, V3 is equal to V4 plus Q3, or V2 equal to V3 plus Q2, or V1 is equal to V2 plus Q1. So these are the values of Q1, Q2, Q3, and these are the values of V1, V2, V3. So the lateral force and shear force distribution is as shown in the figure. Now, solution assuming without considering stiffness of infantry missile. So in the next bit, what we are trying to do, we are trying to analyzing without considering stiffness of infantry masonry. So the fundamental period TA is equal to 0.075 into H raised to 0.75 equal to 0.075 into 12 raised to 0.75, it comes out to be 0.4836. So the moment resisting frame without infill wall is this one. Now the spectral acceleration is type of soil we are assuming as medium soil. For TA equal to 0.4836 into S. SA by G comes out to be 2.5 because TA is equal to 0.4836 S, that is 0.10 less than equal to TA less than equal to 0.55, and zone factor for zone 3 Z equal to 0.16. Importance factor I is equal to 1.0. Response reduction factor R is equal to 3.0 OMRF. So the horizontal acceleration coefficient AH comes out to be ZA, sorry, Z into SA into I divided by 2GR. So 0.16 divided by 2 into 2.22 and I by 3. So AH comes out to be 0.0667. And the base shear is equal to AH into W. So it comes out to be 910.003 kilonewton. Now, the second type of problem, see here, whenever you solve problems on earthquake, one thing you have to remember, you have to always use IS code with you, and also IS 456 also you should refer. So in the second problem, what we have to do, analyze the building frame considered in example one using response spectrum method dynamic with all other data is same. So what we are trying to do, remaining data is same. Only what we are trying to do, we are just using different method. The response spectrum method or dynamic analysis we are doing. In plan, structure is symmetrical about both x and y axis. So the seismic weight will be equal to W1 is equal to W2 is equal to W3. So 1898 plus 380 plus 450 plus 243 plus 648. So it comes out to be 3619 kilonewton. And W4 is equal to 1898 plus 0 plus 450 plus 243 by 2 plus 648 by 2. So it comes out to be 2793.5 kilonewton. Therefore, seismic masses are M1 is equal to M2 equal to M3. It comes out to be 368.91 into 10 raised to 3 kg. And your M4 comes out to be 248.76 into 10 raised to 3 kg. So the floor stiffness without considering stiffness of infill wall, MI of columns IC is equal to 0.45 raised to 4 divided by 12. It comes out to be 3.141785 into 10 raised to minus 3 meter per. Young's modulus is equal to 5000 root of FCK. So 2500 MP equal to 25 to 10 raised to minus 3 Newton per square. Assuming M25 concrete for columns, K1 is equal to K2 equal to K3 equal to K4. So it comes out to be 0.6075 to 10 raised to 9 Newton per meter. Natural frequency and mode shape. This is the mass matrix. As you can see here, M1, M2, M3, and M4 values are designated diagonally, principal diagonal elements, and we are creating a stiffness matrix. So if you solve this stiffness matrix, it comes out to be this way. So the model shape is this way. So, the calculation of modal participation factor. So this is the calculation part, storage level, seismic weight, and mode. So based on the story level 1, 2, 3, and 4, these are the seismic weights. These are the mode shapes, mode 1 and all. So story level is this much, 4321. Seismic weight is this much, 2793.5, 3619, And in the mode 2, 5I2, WI5I2, WI5, these are the values. Modal participation factor P2 is equal to this much. Story level and story seismic weights are in this way, 2793.5, 3619, and 5I3 values is given, WI5I3 values are given. Again, dynamic analysis is somewhat complicated. Even if you look at the problems also, it is looking somewhat complicated. Story level 4321, seismic weight at 123 is same, 3619. And these are the mode shape, modal mass, modal participation factor. So the lateral load QOK acting on this is this much. Mode 1 now. T1 is equal to 0.424 into S or SA by G equal to 2.5. So this comes out to be this much. AH1 equal to Z by 2 SA by G into I by R is equal to Z is how much, 0.16 by 2 into SA by G is 2.5 I by R. So it comes out to be this much. Similarly, mode 2 is T2 equal to 0.148 S. SA by G is equal to this much. UI2 is this much. Mu mode 3 T3 equal to 0.098 S. SI by G is equal to 1 plus number T. So it comes out to be AH3 comes out to be this much. In the mode 4, T4 is equal to 0.082 S, or AH4 comes out to be this much. So lateral load calculation by modal analysis or SRS method. If you see, these are the story heights 1, 2, 3, and 4. The weight at the story 1, 2, and 3 is same. At 4, it is changing. Similarly, here also for mode 3, weight 1, 2, and 3 is same. It equal to 3619 kilonewton. Now, SRSS method. The contribution of different methods are combined by square root of sum of squares using the following relation. Vi equal to under root of Vi square plus Vi2 square plus Vi3 square plus Vi square. Then story lateral forces are calculated. Fi equal to Fi plus So now if you see story level is 1, 2, 3, 4. Vi1, Vi2, Vi3, and Vi4. These are the combined shear force. And this is the combined lateral force. Important note, if you see, since modal frequencies are well separated in the example, the SRS model combination method is sufficient to combine the contribution of each mode. For the purpose of demonstration of QQC method of modal combination and to compare SRS and CQC method, following calculations are carried out. However, CQC method is preferred when modal frequencies are closely spaced. The contribution of different modes are combined by complete quadratic combination method demonstrated in the following calculation. Shear force quantities in each of the four modes can be represented in this way. This is the damping ratio. These are the V1. Now, story lateral forces are computed from shear forces. Q4 is equal to V4 equal to this much. Q3 is equal to V3 minus V4, V2 minus V3, V1 minus V2. So, summary of results from different methods. If you see, these are the values in the above example. V number is equal to this much, 910.03. Base shear calculated as VB bar by VB. So it comes out to be 910.03 divided by 820.63. It comes out to 1.13. Finally, the discharge values of seismic forces values are Q4 is equal to 271.64 kilonewton. Q3 is equal to 294.42 kilonewton. Q2 is equal to 19.83 kilonewton and Q1 is equal to 124.20 kilonewton. So this completes our module 2. Hope you have understood. Still, if they have any queries, you can just drop a message in the comment box. I will reply you, or else you can just mail me at KV University. And even if you can contact me at 8553171859. So I'm stopping the sharing screen. We will start module 3 now because still time is there. We'll start with module 3. So let me first search for module 3 notes. Okay. So I'm sharing the screen. You just tell me whether it is visible to you or not. So the title of the course is Earthquake Resistant Structures. In the module 3, sorry, it should be module 3. The module 3, what we need to study is structural configuration for earthquake resistant design, concept of plane irregularities and vertical irregularities, soft story, torsion in buildings, design provision for this in IS 1893 2002. So what is the effect of infill masonry walls on frames? Modeling concept of infill masonry walls we need to study. Next, we have to study behavior of masonry building during earthquake failure patterns. Next, strength of masonry in shear and flexure. Next is concept for earthquake resistant masonry buildings. Finally, codal provisions. So we'll start with structural configuration for earthquake resistant design. The configuration of an earthquake resistant building should be as follows. How should be the structural configuration of an earthquake resistant building that we are going to study? The building should have a simple rectangular plan. It is the first condition. It is the building should be simple rectangular plan. Normally we are using rectangular plan only, but in some cases due to aesthetic way and all, we will just modify the plan, but it should be rectangular and simple. Next, long walls should be supported by reinforced concrete columns. This is a very important point. How the long walls should be supported by reinforced concrete columns. At short walls, you can avoid the reinforced concrete columns, but long walls should be supported only on reinforced concrete columns because long walls are more subjected to earthquake and they are the one which are bearing the more load. Next, large buildings having plans with shapes like D, L, U, and X should preferably be separated into rectangular blocks by providing gaps in building. See here, as you said, you normally we use rectangular plans only, but in cities such as Mumbai and all, large buildings will have different kinds of shapes depending upon the population. T, L, U, and X shape buildings are also preferred, but these buildings should also be separated into rectangular blocks by providing gaps in between. Buildings which are structurally strong to withstand earthquakes sometimes fail due to inadequate foundation design. See here, we think that we have designed earthquake resistant building as per IS code, so it can withstand the earthquake. But foundation design is also very important. Whenever you design a building, first thing you have to take into account is the foundation, because your entire building is dependent on your foundation. Tilting, cracking, and failure of the structure may result from soil liquefaction. See here, soil liquefaction is also a very important parameter. So the tilting, cracking, and failure of the structure. How is the tilting is occurring or cracking is occurring or failure occurring due to soil liquefaction. So soil liquefaction also you have to be very much consider about. So what exactly is soil liquefaction? Soil liquefaction means transformation of soil from a solid state to liquid state as a consequence of increased pressure. So soil liquefaction means what? Transformation of soil from solid to liquid state as a consequence of increase in pressure. Normally we think and assume that soil is solid. Yes, it is solid. But if some amount of water is inserted into it or due to increase in pressure of the molecules due to Void's ratio, air bubbles and all, what will happen? There will be increase in the there will be change in the state of soil from solid to liquid. Such case is we call it as soil liquefaction. Depending on the type of soil conditions, the depth of foundation should be decided. See here. Type of soil condition, whether it is a hard soil, whether it is a rock soil, whether it is a soft soil, depending upon the soil condition, the depth of foundation should be decided. Now, behavior of brick masonry walls. So, how the brick masonry walls will behave? The masonry buildings are brittle structures. The masonry buildings are not ductile, they are brittle structures. And the ground vibrations are then shifted to inertia forces and they travel through the roof and walls to the foundation. See here, when an earthquake occurs, the horizontal forces and the lateral forces will act on the building, as a result of which ground vibration starts, and inertial force is developed through the roof to and walls to the foundation. A wall topples down easily if pushed horizontally at the top in a direction perpendicular to its plane, weak direction, but offers much greater resistance if it is pulled along its length, strong direction. See here, weak direction and strong direction means wall. If we assume that a wall is there, it will topple down easily if it is pushed horizontally at the top in a direction perpendicular to its plane. So this is known as weak direction. Weak direction of a building is its top wall, but offers much greater resistance if pushed along its length. So why it is offering greater resistance if it pushed along the length? Strong direction, because it is in a rigid state, it is attached to the foundation. So if you see this figure, basic components of a masonry building, this is the roof, this is the walls. So base in the direction of force on the walls critically determines the earthquake performance. In the case it is topping up because it is pushed perpendicular to the plane of the wall. Direction of earthquake shaking is right side. It is pushed in the plane of the wall. Direction of earthquake shaking is in opposite direction. The ground shakes simultaneously in the vertical and two horizontal direction during earthquake. So how the ground shakes during earthquake? It will rotate in vertical direction in one direction, whereas in two horizontal direction during earthquake. Horizontal vibrations are the most damaging. See here, as I said you, horizontal forces or lateral forces are responsible for earthquake. Horizontal vibrations are the most damaging. For good seismic performance, making all walls to act as a box along with the roof at the top and with the foundations at the bottom. Because horizontal forces are more likely to cause earthquake, what you have to do is for good seismic performance, you have to make all the walls to act as a box along with the roof at the top and with the foundation at the bottom. If you assume a box, how it will be? It is open, close at the top as well as at the bottom, and remaining side it is provided with support, what you can say, partitions. So that type only you have to design a building. For the direction of earthquake shaking down, wall B tends to fail. Direction of the earthquake is in this direction and this is failing in this direction. Wall B properly connected to wall A. Roof is not shown. Walls A loaded in strong direction, loaded in weak direction. Tooth joints in masonry cause of L-shaped walls. Direction of earthquake in this direction. So now how to improve behavior of masonry wall. Till now we have studied behavior of masonry walls. Now we will study how to improve the behavior of masonry wall. To ensure box action, connection between walls should be good. Connection is very important. The connection between the walls should be good. Ensuring good interlocking of the masonry courses at the junctions. Apart from this, you have to ensure that good interlocking of the masonry courses at the junction is observed. Next, employing horizontal bands at various levels, particularly at the lintel level. Next, the sizes of the doors and window opening need to be kept small. Connection between walls should be good. Next, sizes of door and window opening need to be kept small, limiting its length to thickness and height to thickness ratio. See here, this parameter normally we will not take into account. Sizes of doors and window is also very important. Thick wall 1/2 brick versus thin wall 1 brick. Overturning because it is thick wall, it is withstanding. Short wall 1 brick, tall wall 1 brick. See here, length is also important, thickness is also important. Here, cross wall, large portion of wall not supported by cross wall, inertia force from roof. In this case, what is happening? Cross wall, short wall, good support offered by cross wall. Cylinder walls are vulnerable. Height and length to be kept within limits. In this figure, the effect of roof on wall is not shown. Choice and quality of building materials. Till now, we have studied behavior of masonry walls and how to improve its strength. Now you will see what is it, how you will decide the choice and quality of building material. Bricks with low porosity are to be used and must be soaked in water before use. Good quality bricks should be used and it must be soaked in water before use. Mud mortar is the weakest, so it should be avoided. 10 mm thick cement sand mortar with lime is the most suitable. Mud mortar we are avoiding. So which type of mortar you have to use? 10 mm thick cement sand mortar with lime is the most suitable. Bricks must be stronger than mortar. This is also very important point. Bricks should must be stronger than mortar. Failure of masonry. The wall may fall straight out in a monolithic piece at a 90-degree failure angle similar to falling tree. The wall may crumble straight down in a so-called curtain fall collapse. The wall may collapse in an inward direction with the top falling inward at the bottom. So different types of failure it is. Failure of masonry, 90-degree failure occurs at fires. The wall falls straight out and top of the collapse. Wall strikes the ground. A distance equal to height of the failing section measured from the base of the wall. The wall begins to lean outward at the top, separating from other enclosing walls and falls straight out at a 90-degree angle. Curtain fall collapse. So how we are defining curtain fall collapse? The exterior masonry wall drops like a falling curtain, cut loose at the top. The wall crumbles and falls straight down with bricks and mortar, forming a pile on the ground near the base of the wall. The collapse of the brick winner Brick cavity or masonry bed stone will often occurs in a curtain fall manier. Which why this type of failure is known as curtain fall collapse? Because the external masonry wall drops like a falling curtain. Inward outward collapse. When a masonry wall becomes unstable and begins to lean inward, it does not always mean that the wall will fall inward. When a section of the broken wall falls inward, the lower portion of the wall may kick outward, or the upper portion may initially fall inward, but then the slide down and outward moves the bottom. So why it is called an inward outward collapse? Both the cases are possible. Normally, we think that if it masonry wall becomes stable and begins to lean inward, it is a inward collapse. But some portion of it is also flowing in the opposite direction, so it is outward collapse. Extras. So by increasing the mortar joint thickness, the strength of masonry will decrease. So how you will increase the mortar joint thickness? The strength by increasing the mortar joint thickness, the strength of masonry will decrease. They are inversely proportional to it. So if you increase the mortar thickness, then the strength of masonry will decrease. So less thickness mortar should be used. The maximum compressive strength of model was obtained when the thickness of the mortar joint was 7.5 mm. So 7.5 mm motor is best suitable. So this almost completes our module 3. In the next class, we will see module 4. If you have any doubts, you can just drop a message in the comment box, or you can even contact me at nadim@cable.university, or you can just call me in the evening hours at 8553 I hope you all have a good time. Thank you, one and all.